If you've ever tried to list a massive collection of objects, say every possible way to schedule a tournament, you know that the sheer number of possibilities can be, well, overwhelming.
It's a huge challenge.
Today, we are plunging deep into discrete mathematics to tackle a classical problem: how to list these complex objects in the neatest, most elegant way possible.
Welcome to this dive. Our focus is on what are called gray codes for a class of objects called multi-set permutations.
And a gray code is, the gold standard for listing things, right?
It is. It's an ordering where every item on the list is just a tiny little bit different from the one before it. A small change.
And we're here to find the dividing line, the precise conditions under which such an efficient listing is even possible.
Exactly.
So the specific small change we're looking at today is key to this whole thing. It's called a star transposition.
Right. It sounds complicated, but the idea is actually pretty simple.
Okay, break it down for us.
Imagine you have a string of symbols, like a password or a code. A star transposition is just swapping the very first symbol in that string with any other symbol later on.
Any other one?
Any other one. It's called star because if you think of the positions as points, the first position is connected to all the others. It looks like a star.
So if I have the sequence 1, 2, 3, 4, I can swap the 1 with the 2.
Yep, to get 2, 1, 3, 4.
Or 1 with the 4.
Right. But you can't swap, say, the 2 and the 3 directly.
Got it. The first position has to be involved.
Exactly. And that's a big difference from, the classic algorithms like Steinhaus, Johnson, Schroeder. They use what are called adjacent transpositions.
Just swapping neighbors.
Just neighbors. Star transpositions are a different beast entirely. We're looking at a much, much wider canvas today.
And that canvas is the world of multi-set permutations.
That's the one.
Can you define that for us?
Sure. A multi-set permutation is just a string where some symbols can be repeated. We define it with a frequency vector, which we call a dollar.
Okay, so like A1, A2 dots, AK dot.
Exactly. Where A's is just the number of times you have to use symbol at all.
So if I had the vector A3, that means I have a string with 3 1s and 2 2s.
Precisely. And this one structure, it covers so many different combinatorial objects. Regular permutations are just where all the counts are 1.
And combinations.
Combinations are just the case with 2 symbols, like A, alpha, beta.
This feels like it's leading us right to a very famous problem in this field.
It connects directly to it. This is really built on the foundation of the middle levels conjecture.
Right, which was posed decades ago.
And it asked this very question, but for a very specific, perfectly balanced case. The case of alpha subsets. 2 symbols, same number of each.
That was the big problem of finding a pass through the middle layers of a hypercube, which sounds niche.
It is, but it was fundamental. And it was solved brilliantly by Torsten Mutze in 2016. He proved that yes, for that perfectly balanced case, a star transposition gray code does exist.
So our mission today is to generalize that. If that specific case works, for which other frequency vectors does it work?
That's the mission. We're trying to find the universal rule for the entire landscape.
Okay, let's get into the analysis. To find a gray code, you're looking for a cycle, a path that visits everything once and comes back to the start. How do you model that?
We use graph theory. We define what's called the flip graph, GOA.
Okay.
The vertices of this graph are just all the possible multi-set permutations for a given $1.
And the edges.
We draw an edge between any 2 permutations if you can get from one to the other with a single star transposition.
So finding a gray code is the same as finding a Hamilton cycle in this graph.
It's exactly the same problem, finding a path that visits every single vertex exactly once.
Now, this sounds elegant, but you mentioned there's a fundamental obstacle right from the start.
There is, and it comes directly from the definition of a star transposition.
Because it always involves the first entry.
Right, so think about it. If a permutation starts with a 1, any move you make
sends it to something that starts with a 2 or a 3 or whatever.
Exactly. You can't have 2 permutations that start with 1 connected to each other. This forces the graph to be what we call a k-partite graph. All the vertices get split into entirely different buckets based on their starting symbol.
And there are no edges inside any of those buckets.
None at all. So any path, any Hamilton cycle has to constantly jump from one bucket to another.
That sounds like a huge constraint. How could a cycle even be possible?
Well, that's where the problem really hits. It's what we call the imbalance problem. The whole thing hinges on the sizes of those buckets.
Okay.
If one of those partition classes, say all the permutations starting with symbol 1, is just too big,
you run out of other places to jump to.
You run out of capacity. It's like having a train schedule with several stations. You can only travel from station A to B, C, or D. If you have more required stops at station A than at B, C, and D combined, you can't make a single loop that visits every stop.
The mass of Station A is just
Yeah.
too great.
The math just doesn't work out. It becomes structurally impossible.
So the researchers needed some way to measure this imbalance, a single parameter.
And this is the critical moment, the key insight. They introduced the parameter delta avant, and it quantifies this balance perfectly. It uses $, the total length of the string, and $, the frequency of the most common symbol. The definition is just. Delta equals minus 201 $.
Wow. That's a stunningly simple formula to govern something so complex. Why $2? Where does that factor of 2 come from?
It's the comparison point.
Yeah.
So the size of the largest bucket, the one starters, is proportional to $0.
Okay.
The size of all the other buckets combined is proportional to N minus $8.
Right.
The whole thing is impossible if $8 is greater than N minus $8.
Boy.
If you just rearrange that inequality, you get $2 is greater than $8, or minus $2 is less than 0.
So delta is just a clean way of writing down that comparison.
It's the measure of that difference.
Which leads us to the trichotomy. 3 clear worlds defined by this one parameter. Let's start with the impossible case.
That's the first regime, where delta is less than 0. This means $1 is so big that the largest bucket is larger than all the other buckets combined.
The mass of Station A is just too great.
Exactly. The research proves this in Theorem 4. Deller has no Hamilton cycle here. It's structurally broken. The imbalance is just too severe.
So we've mapped out the here be dragons part of the map. What about where things actually work?
That is the second regime, where delta is greater than 0.
So the largest bucket is smaller than the rest combined.
Right. A cycle is structurally possible, and the result here is really sweeping. Theorem 7 says that for delta $, the graph is Hamilton connected.
Hamilton connected.
Yeah.
That sounds stronger than just having a Hamilton cycle. What does that mean?
It means you can start and stop anywhere you want. A Hamilton cycle just guarantees one big loop. Hamilton connected means you can pick any 2 permutations in the entire set, and I can find you a path between them that hits every other permutation exactly once.
That's the strongest possible guarantee of a path.
It's the gold standard.
Which leaves the knife edge case.
The boundary, where delta is exactly 0.
So the largest bucket is the exact same size as all the others combined. A perfect, fragile balance.
Precisely. This is the most challenging regime. And mathematically, this is the generalization of the middle levels conjecture. That was a delta $. Case. This boundary is the foundation for everything else.
So let's talk about the proofs. How did they prove those really powerful results for the delta $. world?
They used a technique they call the induction machine. It's a very systematic, top-down approach.
How did that work?
The core idea is decomposition. You take a big, complicated graph, and you break it into smaller, more manageable subgraphs.
Okay.
By fixing a symbol somewhere other than the first position, for instance, you could look at all the permutations where, say, the last symbol is always a 3. What's left over looks just like a smaller problem, a smaller graph.
I see. It's like building a giant Lego wall by first proving that all your individual bricks are solid.
That's a perfect analogy. You assume that these smaller component graphs already have this strong Hamilton-connected property.
And then you stitch them together.
Then you stitch them. You take the Hamilton paths from these smaller graphs, and you carefully link them end to end to form one giant continuous path through the whole structure. The entire process is designed to climb away from those difficult delta $. Cases.
Which serve as the base cases for the induction.
Right.
So the success of that whole beautiful theory for delta,
Right.
It all rests on solving that narrow boundary condition.
It is the central bottleneck. All those strong results are technically conditional on the boundary cases behaving correctly.
And what's the big challenge there at the boundary?
The primary open problem is what's known as conjecture 6. It states that for almost all cases where delta A, the graph must be Hamilton 1 laceable.
Okay, Hamilton 1 laceable. Let's break that down.
It's a very specific property you need when the sizes are perfectly balanced. It means a Hamilton path must exist between any vertex starting with symbol 1, the big class, and any vertex starting with a different symbol.
So you have to start in the big bucket and end in one of the smaller ones.
You have to. It forces a certain kind of path that can actually navigate that perfect balance.
It sounds like the math is forcing a very specific start and end point just to make it possible at all.
That's right. But we have a lot of evidence that this conjecture is true. Theorem 8 strengthened the old middle levels result. We have unconditional proofs for other specific cases too, like in Theorem 9.
And you can just Check it with the computer, right?
To a point. They did. They verified conjecture 6 for all cases where the total string length is up to 8. That gives you huge confidence, but it's not a formal proof.
So given that the induction machine can't get started on its own at the boundary, the proofs there must use a totally different strategy.
A completely different strategy. It's called cycle factor merging.
Okay.
If the induction machine is top-down decomposition, this is bottom-up surgery.
Surgical how?
First, you find a way to cover the entire graph with lots of little separate loops. A cycle factor.
So you break the whole graph into tiny manageable cycles.
Right. Then you pick your start and end points and build an initial path. And then comes the merging.
The hard part.
The very hard part. You have to iteratively absorb all those other little cycles into your one main path. You do it by carefully swapping edges, taking one from the path, one from a cycle, and replacing them with 2 new edges that stitch the cycle onto the path.
So instead of breaking a big problem down, you're starting with lots of little solved problems and figuring out how to weld them all together.
It's a huge contrast in approach.
Yeah.
But it's essential for those boundary cases where the induction doesn't have a solid footing.
And this approach, combining the surgery with the computer checks, actually led to some strong unconditional results, right?
Yeah.
Independent of the main conjecture.
Exactly. This helped address an older conjecture by Shen and Williams. Theorem 10 gives us a powerful unconditional answer for some cases. It says if delta $A and the most frequent symbol count, $1, is small, like 2, 3, or 4, then the graph is for sure Hamilton connected, no conditions attached.
Wait, why only for 2, 3, or 4?
These are the cases where they could computationally verify all the required delta $A base cases. So the computers build a solid, unconditional foundation for those specific values, and then the induction machine could climb up from there, no strings attached. It's a great example of computation and analytic proof working together.
So if I put this all together, we've basically got a complete map of possibility, and it's all defined by that one parameter.
That's the perfect summary.
The territory is either impossible, or it's possible but conditional on the boundary, or it's that fragile boundary line itself.
The structural framework is complete. We know exactly when a star transposition gray cone is structurally viable. That trichotomy, impossible, possible, and the critical boundary is the whole story.
So what's the one thing our listeners should be mulling over after this? What's the future horizon?
The big takeaway is how everything, all those sweeping results for the vast majority of cases, is still conditional. It's all resting on solving that one delicate knife edge problem.
Conjecture 6. Proving that all those delta graphs behave as expected.
Right. If someone proves that one boundary conjecture,
instantly, the entire map for the possible world becomes a set of solid, unconditional theorems.
Absolutely. That one proof would complete the entire puzzle. It just highlights how these huge mathematical structures so often hinge on getting the perfectly balanced, most difficult cases just right.
It's also worth noting, though, the difference between a proof of existence and a practical application.
A crucial distinction.
These proofs show that a path exists, but can a computer actually find it efficiently?
Not necessarily. The proofs are so complex with deep recursion or these intricate merging operations that they don't guarantee an efficient algorithm.
So it's not something you can just code up tomorrow.
Right. Developing a truly fast algorithm, one that can generate the next permutation in polynomial time, that's still a major open challenge.
So proving existence is like drawing a beautiful, complex map of a trail across a landscape.
Yes.
But an efficient algorithm is like building a multi-lane highway along that exact same route.
Yeah.
One shows it can be done, the other makes it useful.
That's a fantastic way to put it. The theory is there, but the fast universal implementation is the next mountain to climb.
A truly elegant look at how a simple rule, the star transposition, creates these deep, complex structures, and how a surprisingly simple parameter unlocks the whole thing. Thank you for guiding us through this.
My pleasure.
And thank you for tuning into the deep dive. We hope you feel a little more well-informed.